Okay, good morning, good afternoon, good evening, everybody. Welcome to session 8 of our EVPN webinar series. So in this session, we're going to dive a little bit deeper into EVPN multicast operation, specifically around what we're now talking about. We talk about EVPN multicast in the context here. We're talking about inside the data center deployment. So, and we're also talking, obviously, when we're talking about data center, we're talking about EVPN multicast with VXLAN encapsulation. Mitch, can you move to the next slide, please? So this, as I say, this is session 8 of our series. Now, some of the concepts we're going to talk about today do leverage what we covered in session 5. So in session 5, we discussed details around type 6, 7, and 8, which are used for the multicast signaling. And we also introduced in session 5 as well the OISM model for layer 3 multicast forwarding as well. So if you want to review that session is still available along with the rest of the sessions, still available for download from the website. But in this session, we're going to dive a little bit deeper. So taking those concepts in session 5, but now dive a little bit deeper into the functionality. We'll talk a little bit about the transport models and the different route types. Now, before we hand over to Mitch, where Mitch is going to go through some configuration detail and operational details and such like, it's probably worth kind of a couple of slides like here covering what problem we're trying to solve, right, when we talk about EVPN multicast. So we're talking here is that where customers we see are deploying obviously EVPN inside their data center. They're used EVPN for their unicast traffic, and they're built multi-tenant environments where providing VRF awareness for unicast traffic. So when we now talk about multicast, they're kind of trying to solve similar problems that they've solved with a unicast deployment with EVPN. They're now looking to solve it a similar way with multicast applications. So what I mean by that is they're trying to produce and deliver multicast in an EVPN environment, but deliver it whereby it's VRF aware. So therefore provide separation of multicast groups and multicast streams across different VRFs or different tenants within the EVPN domain. Key point as well is, like a lot of times when we talk about in the context of a data center, the application, the multicast applications themselves, whether it be video, IPTV, or even data trading, they're either very high bandwidth, as you can imagine, if it's a media, IP media, or it has to be delivered in a fair manner, right? So fair manner means that when the stream is sent across the fabric, we want to get to a point whereby each of the receivers receive it roughly at the same time, right? We don't want any lag or delay between one receiver receiving the flow and a second receiver receiving the flow. So there's a requirement here of delivering not just high bandwidth, but delivering high bandwidth multicast traffic fairly. Now, third requirement is that we're not just talking about layer 2 multicast across the fabric here. We're also talking about providing the ability or solving the capability of delivering layer 3 multicast as well, right? But at the same time, ideally providing a model whereby the multicast is delivered very similar to the way the unicast traffic is routed today. So what that means is delivering it where you can route optimally at the top of the rack rather than having to do some sort of a centralized multicast routing. So a requirement here is to do multicast layer 2, multicast layer 3, but deliver the multicast layer 3 at the top of the rack so it's optimized and delivered efficiently. And then a fourth requirement within all this type of solution is that the EVPN domain itself doesn't exist in isolation. So there's going to be a requirement and a demand for providing access to external sources. So external sources that might reside within a PIM domain, or there might be external receivers within the PIM domain, and allowing connectivity for interested receivers in the EVPN domain, access to those sources that are outside in the PIM domain, and vice versa, right? So whereby there's receivers in the PIM domain, providing them access to sources and multicast streams that are inside the EVPN domain, right? So that's kind of the 4 pillars that we're trying to solve when we talk about EVPN multicast. And how we're going to solve this is kind of, and we'll go into obviously the details of this, but we solve this using some new standards. So we're now where before, if you were delivering multicast in an EVPN environment, a lot of it would be a vendor-specific solution. What we're now talking about is a solution that's based on standards that have been adopted across multiple vendors, right? So you've now got a standards-based solution and providing a solution that's going to be multi-vendor interop. We're also going to talk about, as I say, we talked a little bit this in session 5. We're now going to talk about new route types in the control plane. So there's introduction of the type 6 route, which is going to allow us to start signaling local joins and signal those local joins to the other VTABs that are interested in that join by this new route type 6, so the IGMP proxy route. And 7 and 8 as well, where we talk about, which involved where we have sources or receivers that are dual homed using EVPN all active multi-homing. And what's termed is this ability to do not just layer 2 multicast, but also layer 3 multicast at the top of the rack, right? So what was termed as optimized multicast routing, or OISM is the term that's used. And in this particular solution, when we go into the details of it, we're going to deliver the multicast using a PIM underlay, right? So what we mean by a PIM underlay is that now we're going to take the multicast traffic that's in the overlay, and we're going to then VXLAN encapsulate it and send it to any interested receiver that's signaled via those type 6. But when we do the VXLAN encapsulation, we're going to encapsulate it with a multicast destination, which is in the underlay, and that's where the PIM comes into play, right? And the reason why we do that is that then allows us to deliver the multicast across multiple VTABs in a fair manner, right? So we'll talk a little bit more detail on this. So before we go into that, I'm going to hand over to Russ, and Russ can kind of break down where the different components of this solution sit in terms of the control plane and then the forwarding plane. Over to you, Russ.
All right. Yeah. Thanks, Alex. So yeah, before we get into the detail, this is a view of the control plane and forwarding plane for EVPN multicast, and looking at OISM. As Alex was mentioning, it builds upon the route types that we covered in session 5, the route type 6, and also the active multi-homing type 7, type 8. From a forwarding plane, obviously we're talking about VXLAN encapsulation in this solution. There are 3 transport models: ingress replication, assisted replication, and PIM SSM. And PIM SSM is the one that we are focusing on in this presentation. Actually, I'll just answer, there's a few questions around the EVPN webinar. We have posted the previous webinars up in the chat or in the Q&A. And if you want to access the webinar, you just have to put your email in and you will have full access. So it's all there. The whole series is in, I think was just posted before. So if you go look at the answered questions, you'll see the link there. Just takes an email. Next slide, Mitch. Okay, so 3 really models for the transport, as I mentioned: ingress replication, assisted replication, and PIM transport. Now, in the ingress replication, generally there's obviously no multicast required in the underlay to forward the overlay multicast traffic. However, the burden does fall on the source VTAP. It has to ingress replicate a number of times to however many receivers there are. Obviously not ideal if you want fairness or if you want to reduce or for any sort of high bandwidth applications. You're going to consume way too much bandwidth and there's going to be no fairness. So it's suitable for low bandwidth applications where you just have sort of multicast apps that require segmentation or multi-tenancy for multicast or IGMP in the overlay. However, the flows are not significant. And this is a model that we support in EOS because it is compelling for customers that just want this capability but don't want to turn on PIM in the underlay. The second one is assisted replication. Here the onus really falls on the spine. You send from the leaf and each is up to the spine to determine via signal capabilities that they need to replicate to interested VTAPs. So you still have asynchronous delivery model because you are still replicating at the spine, but compared to the ingress replication model, you're moving this really the same function up to the spine and saving on that upward band length, but it's still still being asynchronously delivered. Where we've worked mostly with the customers and the ones who are compelling us to move forward and want multicast is because they have critical multicast applications that they need in their overlay. Hence, really, the only viable transport there is PIM, because in this scenario, you're efficient use of bandwidth. You are not rewriting multiple times. You're essentially, as Alex mentioned, putting on a destination multicast address and sending. So here it's just relying on, the PIM, replication we know and love for fair delivery. So here you get a lot of fairness, and obviously the suitability here is for high bandwidth, latency sensitive applications. And this is the one we're focusing on here in this this webinar as well, this transport type. Next slide. So focusing on the forwarding plane, and just before I hand over to Mitch, and we'll go through this in all the detail, and you'll see the route types. So in the forwarding plane, obviously relying on a PIM underlay transport. And here you'll see mention of the very important type 10 route. Now, for those from the NG and EVPN world, it's a similar concept. So here you're providing, this route provides the overlay to underlay multicast mapping functionality. And also, as you'll see, as Mitch goes through the presentation, it provides a sort of VNI to multicast address mapping as well. Obviously, VXLAN is the encapsulation still, but now the destination on that VXLAN encapsulated frame packet is a multicast destination address. So this is how the forwarding plane works in this session. We'll be stepping through exactly this. Next, I think that's me. Anything I wanted to add there before we hand over to Mitch, Alex?
No, I think we're good to hand over to Mitch. Yeah.
Yep. In the interest of time, there you go. Take it away, Mitch.
All right.
There will be,
there we go.
Any questions, Mitch? Just throw them up and ask away, and we'll cover them as they're answered.
All right. Yeah. Feel free to interrupt, guys, as needed if I miss something or if there's questions. But yeah, thanks for the intro. And thanks, everyone that has made the time to join our EVPN multicast bonanza today. As usual, we're live, so expect the unexpected. As Alex called out earlier, previous sessions are recorded, and there's a link on the screen. I believe that link was also sent in the chat. So again, pop in your email address and then full access to the webinar series. As Alex called out earlier, the sessions do build upon each other. So concepts covered previously might be lightly touched upon, or they may not be covered at all. So there is an expectation that attendees have some level of comfort with some of the concepts we've covered previously. For today, we're going to have our usual lineup of scenarios, but our scenarios today, they're really going to be based on a list of common questions that come up with EVPN multicast. Because as you may have heard, there could be quite a bit to unpack here, right? So we'll take a look at the configuration, and then we're going to look at all the different control plane components, and then how they all come together to ultimately feed the data plane operations to deliver these multicast feeds in the overlay. And to really kind of unpack this effectively, we're going to spend a lot of time on the whiteboard today. We're still going to hop into the CLI. We may do a packet capture here and there. Maybe a couple questions come up. We want to validate the data plane. But a majority of our time is going to be spent on the whiteboard today, kind of unpacking all this. So here's the list of questions that we're going to run through. They'll set the stage for each respective scenario. And so we have 8 questions in roughly, we'll call it 45-ish minutes to get through. Since this is the last webinar in this series, maybe we go out with a bang and we blast right through that 1 hour time limit, or maybe we skate across the finish line right at an hour. One way to find out. Let's jump in. All right, so for the first question, this is really where it all starts. There's all this discussion about underlay PIM transport, and we're going to hear the terms underlay and overlay a lot today. All right, so first, how do we really configure that underlay PIM transport? And really, as called out here, it's a 2-part answer. First, we're going to enable multicast routing globally, so in the default VRF, on the spine switch, as well as all of the VTEPs that we're going to be providing EVPN multicast services on. We're also going to enable PIM on the underlay interfaces of these devices. So at that point, multicast is running, and then what we should see is that there are PIM adjacencies in the underlay on our spine, right? So to all of the VTEPs that we plan on using to provide EVPN multicast services, we want to make sure that in the underlay that it is PIM enabled and that those VTEPs have a PIM neighbor adjacency with the spine. All right, we're doing pretty good so far. That took maybe a minute. We're doing pretty good. So how do we configure the underlay PIM transport? Well, we configure it. We enable PIM on the interfaces, and we enable multicast routing globally in the default VRF. Now, again, we're really setting the foundation here. We haven't discussed anything VXLAN or VRF related. We're setting the foundation with the PIM underlay for the transport of that overlay multicast traffic. All right, so next, and we'll pause for some questions after the second question. But next, there's a term that was used really quickly earlier, bull traffic. And I want to drill into what is that. So what is bull traffic and how do we actually forward it? And in short, previously we had the term BUM traffic, so broadcast, unknown unicast, and multicast. And we're really swapping out the M in BUM and just swapping it out for LL, so link local traffic, because as called out, we're going to be forwarding multicast and the overlay differently than we're going to be forwarding, for example, ARP requests that are sent from attached hosts. So what's BUM? Now it is the broadcast, unknown unicast, and link local traffic. So first, on a per bridge domain basis, the level of EVPN support, EVPN multicast support, so EVPN multicast capabilities, it's going to be signaled via the IMET route, right? So this IMET route is the IMET route we've been discussing since the initial webinar. You got a fresh coat of paint, a little bit of an update here, and it's specifically around the multicast flags. So if the VTEP supports EVPN multicast capabilities for the bridge domain, or maybe the VRF, which we'll dive into in a minute here, it will set the appropriate multicast flags in the extended communities field of the IMET route. Now, for example, it may say, hey, I support the IGMP proxy route or the SMET route, which we'll dive into. But also it's going to say, okay, well, for bull traffic in this bridge domain, how do we want to handle that? Right, so down here, we have this tunnel type. And in the PMSI attribute, so this tunnel type, we can leverage ingress replication, we can leverage PIM. In our scenarios today, we're going to leverage ingress replication, but if we wanted to support PIM, we could absolutely do that as well. So seeing how this route is actually advertised from the VTEPs, assuming all of these VTEPs, leaf 1 through 6, have the bridge domain VLAN 10 locally present, they're going to, of course, originate a type 3 route associated with that bridge domain. And a lot of this looks like what we've seen thus far throughout the webinar series to this point. We have the route distinguisher associated with the bridge domain, the RT, but now we also have the multicast flags, right? So if we support things like IGMP proxy, we will signal that in the IMET route. And then last but not least, we have the tunnel and the tunnel ID indicating that, hey, for bull traffic in this particular bridge domain, we're going to leverage ingress replication. So head-end replication, ingress replication, whatever you want to call it. And this route is, of course, still used to populate the flood list. So leaf 4 receives the IMET route from the other VTEPs and says, okay, well, I now know that those are the remote VTEPs I should add to my flood list for bridge domain VLAN 10. So we'll quickly kind of see this in action. Let's say host 4 down here, he sends, let's say it's just like an ARP request, something, some sort of broadcast. Leaf 4 is going to send a copy of that to leaf 1, create another copy, send it to leaf 2, leaf 3, 5, and 6, as expected, right? So nothing really unusual or different than what we've seen thus far in the webinar series to this point. For the broadcast on a unicast traffic, we're still just leveraging ingress replication in this case. Even though we do have the option of PIM, we're still leveraging ingress replication. So we'll quickly summarize this and then we'll pause for some questions before we get into actually enabling EVPN multicast. But big takeaway here is that it's no longer just BUM traffic because multicast traffic is going to have a different forwarding methodology. It's now broadcast, unknown unicast, and link local, aka bull traffic. In our scenario, we saw that we are transporting this via ingress replication or head-end replication, whichever term you'd like to use. But again, we could use PIM for transport if we wanted to. Yeah, EOS does support this. And last but not least, the multicast capabilities, so the EVPN multicast capabilities are signaled via the type 3 IMET routes associated with a given bridge domain, or in the case of, as we'll see in the supplementary bridge domain, the VRF. All right, so Alex, Russ, any questions out there or anything you guys would like to add?
Sorry, Mitch, there is one question, and I think you might cover this later on, but there was discussion here, question around the underlay itself. what was then talked about, you're running PIM in the underlay.
Correct.
Where would the RP then be positioned in this
Ah,
environment?
that is an excellent question. That is an excellent question, and then we just may be getting to that later on in the presentation. So, yeah, that's an excellent setup. We will get there.
I'd say
Okay.
just for clarification with what we're showing here, essentially the multicast, the way the multicast traffic is dealt with is essentially separated out. Bull traffic is dealt with one way by the PTA, and the other one is signaled in the IMET route saying, by the way, I'm multicast capable in the overlay. So this whole section is sort of showing that these two are separated out now and dealt with in different methodologies. So just to summarize.
Cool. All right, we will definitely get to the RP question. All right, so next we'll jump into question 3. Mainly, so how do we enable this to begin with? So on the VTEPs, where we actually want to provide the EVPN L3 multicast or OISM services, how do we turn this on? And this is, here's the config. I know we talk a lot in this webinar series about know the protocol, not the config. I think this is probably one of the greatest examples of that. If anyone's looking at this and going, wow, that's actually less config than I thought would be required for this. I feel the same way. So ultimately what we're doing is we are going to enable multicast routing for the VRF, in this case, VRF-A. Once that's in place, then we're going to map an underlay. We're going to map a multicast group, specifically an underlay multicast group, to the VRF, right? So this bears repeating because this is going to be a really important concept. This group is going to be used by leaf 4, or whatever leaf or VTEP we're configuring this on, to send overlay multicast traffic in VRF-A into the PIM underlay, so into the EVPN domain for transport. All right, so we're going to spend a lot of time talking about that today, but just know that this is an underlay multicast group mapped to the overlay VRF for transport across our underlay PIM domain. Then last but not least, we're actually going into the VRF and we're hitting the on switch. So EVPN multicast, go. So this is the configuration, and really kind of like the work starts once the configuration is in place, because then we'll get to take a look at the control plane and see what happened. Right, so when we put this configuration in, what actually ended up occurring? And we'll kind of walk through this on the whiteboard, but first we'll set the stage with some concepts. First, some new routes were generated, specifically the type 10 routes, which Russ alluded to earlier. Now, the type 10 route is going to serve 2 primary purposes. The first is going to be to signal the overlay to underlay multicast group mappings to remote VTEPs for a given VLAN, or in our case, for a VRF. I was just going to say, hey, just so everyone knows, when I send traffic out into the EVPN domain, into the PIM underlay, if it's a overlay multicast feed in VRF-A, I'm going to send to this group. And that was, for example, this group that we mapped on leaf 4 to VRF-A. So the type 10 route is going to be used to communicate these mappings amongst the VTEPs, and we'll see how this is used in a minute. Next, it's actually going to map bridge domains to what's referred to as the supplementary bridge domain, or the SBD. In other words, it's going to provide the VTEPs with the way to map VLANs to VRFs, even if they don't have that VLAN locally present. So even if a VTEP doesn't have VLAN 10, it'll be able to use the type 10 route to then understand, okay, which VRF does this particular bridge domain actually map to? Right, so as it calls out right here, more on this soon, that's going to have to do with how receiving VTEPs actually forward the feeds to their locally attached receivers. But just remember these 2 primary purposes of the type 10 route. 1, overlay to underlay multicast group mappings. And then 2, mapping VLANs to VRFs amongst all the VTEPs. And then next, when we enabled EVPN multicast under the VRF, it actually ended up creating that supplementary bridge domain. So we're going to talk much more about the SBD later and how it's ultimately used. It'll a little bit of foreshadowing. It'll be an answer to one of our questions. But for now, we just need to know that it exists. And ultimately, it's just another bridge domain. It just so happens to have no attached interfaces. So this SBD, notice we didn't explicitly map it in our config. We didn't say, hey, VLAN X maps to VRF-A as the supplementary bridge domain. It actually just assumes the route target and the route distinguisher of the IPVRF that it was mapped to. And it uses whatever dynamic VLAN behind the scenes was mapped to the L3 VNI of the VRF. So we don't need to do this, but it's good that we know that it's there, right? And we'll show some commands on how to validate this. So for now, just know that this is a key part to one of our later questions. All right, so what does a type 10 route actually look like? So what are the contents? Here we have enabled EVPN multicast in VRF-A on all the VTEPs. So the 1, 2, 3, 4, 5, 6. They all have EVPN multicast command under VRF-A in their BGP config. Once that happens, and we have the group mapping under the VXLAN interface, then they generate the type 10 route and say, all right, well, for this particular VRF, so whatever VRF is mapped to this particular route target, in this case, VRF-A, any overlay, anybody sending to anything in this VRF, I'm going to encapsulate VXLAN encap that multicast feed, and I'm going to send it out to this group in the underlay. So the better way to represent this would be like this, right? These are the S, Gs that each respective VTEP will use to send overlay multicast traffic VXLAN encapped into the underlay. And we'll dive into some packet captures and some packet formats to actually show this on the wire. So next, we're going to see a type 10 route also advertised for each respective bridge domain that's present on the VTEP. And we're in this case, we're going to see that the route target of the bridge domain, as well as the route target of the VRF that it's associated with, is going to be present in this update. So this is how all the VTEPs, whether or not they have a bridge domain locally present, this is how they're going to be able to map L2 VNI of 10,010 to VRF-A, or L3 VNI 50,001, however you want to represent it. All right, so every VTEP is going to originate these routes. So there's one for VLAN 10, Leaf 4 sends out one for VLAN 20, maybe Leaf 2 sends out one for VLAN 30, so on and so forth. The idea here is that by the time all of these routes have been advertised, all the VTEPs that have received these type 10 routes now understand what VRF each respective bridge domain ultimately maps to, because this will be important for forwarding operations that we discuss later on. And so the next question is, how do we actually see this stuff? So the type 10 routes are there outside of doing show BGP EVPN route type, type 10, SPMSI. Can we just run a show command to see what those mappings were? And the answer to that is yes. So if we go on Leaf 1 over here, and we're like, hey, Leaf 1, what overlay to underlay multicast group mappings have you received via type 10 routes? And that's what this command will ultimately give us. So Leaf 1 sees that, okay, well, I received type 10 routes from all of these different VTEPs saying that when they send a overlay multicast feed out into the PIM underlay, so they VXLAN encap it and send it out into the PIM underlay, they're going to send it from their own source address, so 2226, for example, and then they're going to send to the group 232.0.0.1. In other words, if I want to receive overlay multicast traffic in VRF-A, I better join these groups. All right, and we'll see in a minute how that actually happens. The next, if we want to validate the mapping of bridge domains to VRF, even if we don't have that bridge domain locally present, we can validate that by saying show VXLAN VNI. And this will show our dynamic mappings, even though we didn't statically map any bridge domain to this VNI on Leaf 4, for example, or Leaf 3, we still have that mapping in place. So we know that this bridge domain maps to this SBD, maps to this VRF. And then same thing over here on Leaf 1, VLAN 20, which doesn't exist on Leaf 1, maps ultimately to VRF-A. And then finally, to kind of wrap this up a little bit as it relates to the kind of SBD here, if we want to see the instantiation of that supplementary bridge domain, we can just run a show BGP EVPN instance command for the supplementary bridge domain of VRF-A, and then this gives us all the information. So as expected, this supplementary bridge domain is associated with VRF-A. It assumes the RD and the RT values of VRF-A. And then also it is VLAN based. And we know based off what we discussed so far that the VLAN that this is associated with is whatever VLAN was dynamically associated with the L3 VNI mapped to the VRF. All right. And we'll just talk about this one real quick. The supplementary bridge domain. This is really just driving home the point that it's just a bridge domain. So even though it has no locally attached interfaces, it still behaves like a bridge domain. And as a result of that, an IMET route is generated for it. So we will see an IMET route generated for the SBD that has the route target of the IPVRF. And then we'll also see, of course, the multicast flags in there as well. So like IGMP proxy, OISM support. In this case, kind of do some foreshadowing here, the PEG, which came up a little bit earlier. We'll talk about the PIM Edge gateway later on. But those capabilities are all advertised using the multicast flags in the IMET route. And if we want to see that on the wire, here it is. So multicast flags in the extended communities field. We have the route target of the IPVRF, the route distinguisher that this particular VTEP uses for that IPVRF, and ultimately the L3 VNI. All right. So that actually wraps up question 3. Just really want to reiterate the importance of that type 10 route. All right. So we enable multicast routing for the VRF. We enabled EVPN multicast by hitting that on switch, saying, all right, under the VRF, EVPN multicast, go. So that created the supplementary bridge domain. But ultimately, we really drilled into this. It resulted in the generation of type 10 routes. And those type 10 routes serve 2 very important purposes. The overlay group to underlay multicast group mappings, and then the bridge domain to supplementary bridge domain, or probably better put, VLAN to VRF mappings. And then last but not least, for the supplementary bridge domain, it really is just another bridge domain. As such, we saw an IMET route advertised for it, and we saw some multicast flags in there. So before we keep going, I do want to pause because I know that with the type 10 route at first, at least for me, it can be like, wow, that's quite a bit of info, but this is really the 2 big takeaways here with that route. I do want to pause for questions or Alex, Russ, anything you guys would like to add to this?
Yeah, just actually 2 questions, Mitch, that came up. So one question that came up is the actual multicast underlay group. I know in your setup, you have the same multicast group for the same VRF across all the VTEPs. So the question really was, is that required, or could I potentially configure a different multicast group on each of the VTEPs in the same VRF?
Oh, okay, good question. It is not required. So if we wanted to go in and actually create, for example, let's go ahead and look at that show output again. If we wanted to go in and say on leaf 4 or 5, 3, whoever, and use a different multicast group mapped to the VRF under the VXLAN interface, we could do that. So these, in our example, are the same, but they don't have to be. We can use different multicast groups if we want to in our deployment. Anything you want to add to that, Alex?
No, I think that answers the question. And then the other question that was raised, Mitch, and I think you had it in your summary slide anyway, but so the question was, you said that the supplementary bridge domain was a logical bridge domain without any locally attached circuits. So the question then was, well, if it's generating an IMET route, how do you configure the RD and RT for the IMET route?
Oh, yep. Yeah, good question. And it just automatically assumes the RD and the RT values of whatever VRF that particular SBD is associated with. So in our case, we created one for VRF A. And then because of that, the SBD associated with VRF A then just assumed over here the route distinguisher and the route targets associated with VRF A. Actually, we can take a look at this, probably better off in the environment here. If we look at leaf 1, show run section, router BGP, we look at VRF A, we have an RD of 111, 50,001, and then we have our route targets over here. So this is the IPVRF. If we look at our show run into VX1 interface here, we have VRF A as mapped to L3 VNI 50,001. Okay, we've had that for a while, but in our webinar series, but this is new today. We're mapping the VRF to that underlay multicast group. right? So we enabled EVPN multicast. That then told the VTEP to, okay, we're going to create a supplementary bridge domain, OBGP, EVPN instance, SBD-A. We created the SBD, and it just automatically assumed the route targets and the route distinguisher that were associated with the IP VRF. And one more thing, this actually kind of helped me kind of drive this point home because this was a bit confusing at first. You know, what VLAN is the supplementary bridge domain? It's whatever VLAN was dynamically associated to the L3 VNI when we put in this command here, right? So we went into interface VXLAN 1, we mapped VRF-A to L3 VNI 50,001. Well, behind the scenes, a dynamic VLAN is associated with that VNI, even though we don't explicitly do it. So in this case, we have VLAN 4093 associated with VNI 50,001. 4093 on this particular VTEP is going to be used as the supplementary bridge domain, the SBD. So I know that was more detailed than the question was asking for, but those are some things that did help me kind of tie this all together. Make sense?
I think, yeah, I mean, that makes perfect sense. And there have been a few questions on this and what's the route type 10. So if you know, when you look back at this and at this webinar, and you showed it, Mitch, it's really, why is it required? But it's sort of common questions. I mean, it's required because not the same multicast address could be on every leaf. So, you know, that's part of the information that's gleaned from that type 10 route. It's the underlay to overlay mapping, which, you know, as we've seen, could be different. And also you mentioned the VNI to VLAN mapping. These are not locally configured. You showed it when in that first one, like the VNI 10 is not, I believe maybe whichever one, okay, VNI 40 is not on this leaf. So how did it get that mapping? That was also from the type 10 route. So those are the two functions of this type 10 route, right? So just to sort of reiterate why it's required, it provides that dynamic mapping.
Yep.
Okay.
Very good. Good question. So good question so far. Any other questions out there? Anything else you guys want to add before we keep on rolling here?
I think we should keep going, man. We're still in the control. We're still in the control plane.
All right, we're getting there. We're getting there, guys. All right, question 4. In the interest of time, it's a 2-part question. So, how do the VTEPs know what underlay multicast feeds to join? Right. So, if a VTEP says, "Hey, I have locally attached receivers. I want to receive overlay multicast traffic for VRF-A," well, what groups do I need to join in the underlay to get that traffic? And the answer, I mean, it's right here, the type 10 route. Again, that type 10 route gives us it's kind of like the decoder ring. It gives us that overlay to underlay group mapping that the VTEP can use to make sure that it joins the proper underlay multicast groups to receive overlay multicast traffic. All right, so kind of one more time, that is so critical. It gives the VTEP the list of underlay multicast groups to join in order to receive overlay multicast traffic. So that is a big responsibility of that type 10 route. But then we don't necessarily want the VTEPs just joining those groups just because they have that local VRF present. We don't want them receiving the feed unnecessarily if they don't have any receivers. So when do they join those underlay multicast feeds or groups? And the answer to that is when they actually have a locally attached host that sent an IGMP join. In other words, they have a locally attached receiver in that particular VRF that wants to receive a multicast group or feed of some kind. All right, so let's look at this in action. We'll kind of walk through this on the whiteboard here. So we have leaf 1 has a couple interested receivers. One's in VLAN 10, one's in VLAN 30, and they're going to send their IGMP join. All right, so they want to join ASM join for 239.11.104. We don't care who's sending it. Give us this feed. So leaf 1 gets this, and it says, all right, well, I know I have local receivers in VRF-A that want to get a multicast feed from VRF-A. Well, now I got to ask the question to myself, okay, what underlay groups do I join to make sure I get multicast traffic for the VRF-A overlay? And it says, oh, well, I'll use the type 10 routes. So you got the type 10 routes. This gives me the list of groups. So if this is over here, this is the source, this is the group. This gives us the list of groups that we should join to get that overlay multicast traffic for VRF-A. right? Because like, for example, if a sender is attached to say leaf 4, leaf source address and the outer IP header of his VTEP IP and a destination address of the multicast group. All right. It looks like my Zoom just told me my internet connection is unstable. Can you guys still hear me?
You are back now. Yeah, you did disappear for a while. You're back.
Okay.
Just
How long was I gone?
A second or two.
A second or two. All right. So we kind of reiterate here. Leaf 1 receives the IGMP joins, the membership reports, and says, okay, well, I know I have locally attached receivers in VRFA that want to receive multicast traffic. What underlay groups do I have to join to make sure I get overlay multicast traffic for VRFA? And it knows that, again, the type 10 route is really the decoder ring for this. It knows that, okay, well, if, for example, leaf 4 has a locally attached sender, it is going in VRFA, it's going to take that sender's multicast feed, VXLAN encapsulate it, and in the outer IP header, when it sends it out into the EVPN domain, into the underlay, it's going to have a source address of its VTEP IP and a destination address of whatever underlay multicast group was mapped to that VRF. All right, so what happens next is the leaf then knows, again, let's take one step back. The leaf knows what groups to join from the type 10 routes. Next, it just joins those groups. So here is the group. In this case, it's 5 joins. So here are all these senders, and then here's the group. So ultimately, leaf 1 is joining all of these S, G groups because leaf 1 has no idea where is the sender going to be located. No idea. It could be leaf 2, 5, 4, 3, who knows, right? So it says, all right, well, to guarantee I get the multicast feed in VRFA and the overlay, I'm joining all these underlay groups. And I know to join these groups because the type 10 route told me so. And the spine then says, okay, great. Well, thanks for sending those PIM joins, leaf 1. If I see this source to this group, or this source to this group, or this source to this group, you guys get the idea, one after the other, I'll make sure that the interface that I received your PIM join on is added to the OIL for this particular group. In other words, leaf 1 will receive that VXLAN encapsulated multicast feed. All right, so we're going to summarize that, and then we'll pause again, and then we'll keep on going. And so again, it really was a two-part question. So how do they know, the VTEPs know what underlay multicast feeds to join in order to receive the overlay multicast traffic? And the answer is, again, the type 10 route. Very critical route if you haven't picked up on that. So the type 10 route gives those overlay to underlay group mappings. But then we don't want the VTEPs to just join those groups just because they got the type 10 route. It'd be nice if they would just join the group only when they have interested receivers in that particular overlay VRF. So as we saw, leaf 1 didn't actually send those joins out until it actually had an interested receiver active in VRFA. Then it joined those groups. And then that way it knows that, well, if there's any sender out there in this VRF, I'm going to get the feed. All right, Alex, Russ, anything you guys want to add to that before we keep rolling?
Yeah, so that you just kind of covered one of the questions I'm typing an answer to. Just to be clear there, so what you just mentioned there, right? So when you have a local receiver for a particular group in the VRF, so just clear what groups you're joining the underlay, right? So you're going to join the groups, each of the SGs to each of the other remote VTABs that are part of that VRF, right? For that multicast group. You want to clear that up?
Yeah. So we can actually let's show it.
So I can answer my own question there, Mitch. Sorry.
You're good. Let's show it. Let's do this. Let's go on the spine. Let's go over here. So show IPM route. All right. We haven't joined really much of anything yet. So do show multicast IPv4, EVPN, decap, right? So this is, received. These are the mappings that we received from the type 10 routes. That's received. Which ones have we joined? None, because we have no locally attached interested receiver. if we throw a watch at the very beginning of this command, do you guys still hear me? Nope.
Yep, we can. Yeah.
Okay, there we go. There we go. All right, so if we go in here now, and let me actually reconnect to Leaf 1, it looks like, again, live, anything can happen. So let's copy this command. We're going to run a watch command on it. There we go. So watch, run this command. There we go. And we're going to actually send a join and say, hey, we're interested in whatever feed. Now we see, aha, it has joined those particular groups. Now if we do show IP mroute on Leaf 1, ta-da, it has actually joined these particular S, G groups in the underlay to make sure that it gets the overlay multicast feeds in VRFA. So again, I know we went a little bit beyond the question, but I hope that was helpful. Alex, Russ, anything you guys want to add to that?
Nope, I think you answered the question and showed that that's CLI.
Okay, cool. All right, yeah. When in doubt, let's take it to the CLI. All right. So next, so the VTEP that actually has the locally attached sender, how does that VTEP know when to send that overlay multicast traffic via the PIM underlay transport? So in other words, just because there's a locally attached sender, am I just going to, anytime I receive that locally attached sender's feed, VXLAN encapsulate it and send it out into the underlay? Or can I just wait until there's actually someone out there that cares about that feed? And the answer is the latter. So once the VTEP with a locally attached sender receives a type 6 SMET route, also referred to as an IGMP proxy route, once that route has been received, then it will say, oh, well, someone out there wants this particular overlay multicast feed. Let me VXLAN encapsulate it and then send it out into the underlay with whatever, in whatever destination multicast group I map to this VRF. All right, so let's actually go ahead and take a look at this in action to kind of really drive home the concept. So again, we have interested receivers attached to Leaf 1, and we have interested receivers attached to Leaf 3. These interested receivers send their IGMP membership report. In this case, it is an ASM join for 239.11.104 in VRFA. So all these guys up here, they're all in VRFA. So Leaf 1 and Leaf 3 receive that. Once they receive that IGMP membership report, that join, they are going to originate a type 6 route, an SMET route, associated with that join that they received. And this route it's going to include, hey, in this particular VRF, there we go, pen's working. So the VRF associated with this, which we know is VRFA, I have locally attached hosts that are interested in receiving the multicast group, the feed of anything to 239.11.104. All right, so if you are a remote VTEP and you receive this and you look at it, you say, oh, well, if I have any senders in VRFA come online and start sending to this particular group, I better make sure I VX and encapsulate that and send it out into the PIM underlay transport. Now, another takeaway with this route is that even though we received 2 different IGMP joins in VRFA for the same group, we only generated 1 route. So there could be 2 hosts here, there could be 5, there could be 100. There could be as many hosts as we like here, generating these IGMP joins for this particular star comma G. But if the IGMP version and the group, the S comma G, is the same, we only generate 1 SMET route. That's why it's referred to as the IGMP proxy route. We're not generating on a one-to-one basis here. All right, so same thing with Leaf 3. So that SMET route is received by, in this case, let's say Leaf 4. And Leaf 4 then says, oh, okay, well, I need to make sure that if I see in the overlay VRF associated with this VLAN, which we know is VRFA, that's the SBD in this case, if I see anyone sending to this group, I better make sure I send that out into the underlay using my PIM tunnel. In other words, VXLAN encapsulate it, source address of my VTEP IP, destination address of whatever we map to the VRF, which in this case was 232.0.0.1. So to really bring this together, let's take a look at what happens All right, so what's the resulting flow? In this case, conveniently, host 4 has come online. How nice of him. And he's going to start sending a feed. So he's sending to that 239.11.104. All right, so leaf 4 sends it out. And the spine, because leaf 1 and leaf 3 have sent their PIM joins based off their received type 10 route to the spine saying, hey, I need to make sure I receive the underlay multicast group 2.2.2.4, comma 232.0.0.1. The spine knows, okay, cool. I need to send a copy of this VXLAN encapsulated packet to both of these VTEPs. And to really kind of drive this point home, let's look at it on the wire. All right, so the host 4 sent the traffic. Leaf 4 knew that there were VTEPs out there with locally attached receivers in VRFA interested in this feed. He knew that because of the SMET route. Because of that, he knew that, well, if I see someone sending to this feed in VRFA, I better VXLAN encapsulate that overlay multicast feed, which is this information right here, and send it out into the underlay with a source IP of my VTEP address and a destination IP of whatever multicast group I've mapped to the VRF to be used for underlay transport. All right, so this, if we represent this a little bit differently, if we look at this and say, this is the S, G, this is the group that leaf 1 and leaf 3 joined, among others, in order to make sure they get a copy of this feed. When they receive it, they do the decap operation, and then they forward it, the multicast feed, in the inner IP header to their locally attached hosts, right? But takeaway here is that leaf 4 only knew that there were interested receivers behind remote VTEPs because those remote VTEPs generated an SMET route for this particular group. All right, if we'll look at the MRoute table here, then we'll pause for some questions. So MRoute table here in the overlay for VRFA on leaf 1. Notice that it says, okay, well, I now know that 10.10.10.104 is sending to this group, and the incoming interface in this case is VLAN 10. That makes sense because the L2 VNI used here in the VXLAN header is 10,010, which leaf 1 has locally mapped to VLAN 10. So incoming interface VLAN 10, it bridges it out to interested receiver 1 in VLAN 10, and then it routes it and then bridges it out to the interested receiver in VLAN 30, which is why we see that in the OIL here in the outgoing interface list. Over on leaf 3, things look a little bit different, and we're doing a little bit more of foreshadowing here. The incoming interface is not VLAN 10, right? So VLAN 10, VNI 10,010 is used in the VXLAN header. Well, leaf 3 doesn't have that VNI mapped to anything, right? So bridge domain 10, which is mapped to that VNI, does not exist on leaf 3. So the incoming interface can't be VLAN 10. In this case, it's VLAN 4094, which we know is the SBD. So more on this in a minute, but that was one key difference I wanted to call out. Over here, the bridge domain exists, so we see it as expected as the incoming interface. But on leaf 3, it's different. VLAN 10 does not exist, so the SBD is shown as the incoming interface. All right, so one more time, the VTEP with the locally attached sender in VRFA only knew that it needed to send that overlay multicast feed, VXLAN encapsulated into the underlay because it received an SMET route that indicated there was one or more receivers behind remote VTEPs for that group. So any questions or anything you want to add, Russ, Alex, before we keep going? I just looked at the time, 1:58. We're doing good, guys. Anything you guys want to add?
Doing good. Yeah. There's one question that came up there, Mitch. So you talked about forwarding the traffic from the source VNI to the remote VTAP that has an interested receiver. So one of the questions that came up is, well, if you're doing that, is the TTL not then decremented? And therefore, is it not look like a packet?
That is a great, great question. We're actually going to dive into that next. The answer is because the routing operation, so this is more of a bridging operation here. The routing operation into the destination subnet or bridge domain. So for example, VLAN 30 over here, that routing operation is done at the egress VTEP, right? So if the receiver is in VLAN 10, there is no source MAC rewrite, there is no TTL decrement. So that's the idea there. That's why we use the L2 VNI associated with the bridge domain of the sender on the sending VTEP, because then we're not decrementing the TTL and we're also not doing any rewrites of the source MAC address. Now, if a routing operation is needed at the receiver VTAP on the egress side, of course, that routing operation will occur. The TTL will be decremented by 1, and the source MAC will be rewritten. But the idea there is that we're not doing that twice. Like, if you remember with unicast and symmetric IRB, there's a routing operation at the ingress VTAP and then another routing operation at the egress VTAP. Here it's different. The routing operation only ever occurs at the egress VTAP. And the idea there is, again, we don't want to unnecessarily decrement the TTL, and we also don't want to unnecessarily do a rewrite of that source MAC in the inner Ethernet header. Anything you want to add to that, Alex?
I think that's good. I mean, essentially, there is no TTL decrement as it goes via the SPD and for routing, right? It behaves as you'd expect multicast, one route, one TTL decrement when you go into the VLAN.
Yep.
Okay, I think we're good.
All right. All right, we'll keep on going here. So the next thing is, okay, how does the VTAP forward those received feeds to its local receivers? And the answer, as we just saw, is it depends. Right? The question was, that was a perfect setup, actually. So thank you, whoever asked that. The L2 VNI associated with the sender is used in the VXLAN header. So what if that receiver VTAP doesn't have that, that VNI locally present? Someone put Rutro here, whoever that was. Thank you. What other Easter eggs await us? But let's go ahead and jump in and let's see what happens. How do we handle this? So host 4 again came online. He's sending to this feed in VRFA. We know that that is going to be delivered via the underlay. So PIM underlay to leaf 1. Leaf 1 gets it and says, hey, I have a local static mapping for VNI 10,010. That's VLAN 10. I'm all set. I'm going to locally bridge that out to my interested receiver in VLAN 10. And I'm going to locally do the routing operation and bridge it out to the interested receiver in VLAN 30. All good, right? Pretty straightforward. And that's also why we see the incoming interface for this multicast group in VRFA as VLAN 10. But what about leaf 3? Poor leaf 3. It says, well, yeah, thanks for this VXLAN encapsulated packet, but I don't have VNI 10,010 locally instantiated, or as someone put on the slide before this, Rutro. But wait, I do have those VLAN to VRF mappings that we learned from the type 10 route. So yet again, the type 10 route saves the day. So we know that, okay, well, even though we don't have VLAN 10 or anything mapped to the VNI of 10,010 locally present, we do know, because of the type 10 routes, that if we are to receive a VXLAN encapsulated packet, we have here the multicast destination address and the outer IP header, we know that this maps to VRFA. So in other words, we can use the supplementary bridge domain, or SBD, associated with VRFA to do the routing operation into the destination subnets where our locally attached receivers reside. And that's exactly what leaf 3 does. So it says, okay, cool. I have that mapping. I know we can use the SBD to locally route into the destination subnet. And then once it's there, we can bridge out to the interested receiver. But it was only able to do this because it knew that this VNI, this ultimately represents a bridge domain that maps to VRFA. So we can do the routing operation using whatever SBD is mapped to that VRF. And then this output should make a little bit more sense now. Now that we know that we're going to be using that supplementary bridge domain to ultimately route that traffic to our locally attached receivers in VRFA, the incoming interface being VLAN 4094 makes a bit more sense now, because we're going to receive it in on the supplementary bridge domain that is associated with that particular VNI that we saw in the header. All right. So we don't need to really read through this slide line by line. We can keep going to the next question. But before we do that, I do want to pause. Alex, Russ, does that make sense? Or just anything you guys want to add to that?
No question on my side, Mitch. Russ?
No, I think we're good. Let's go.
All right, we're cooking. All right, this came up earlier, and we said it was a bit of foreshadowing, which is true. So where's the rendezvous point? And there is no RP. There is no spoon. So at least not in the EVPN multicast domain. All right, so we're going to talk about the PIM edge gateway, or the PEG, next. But remember, these joins that these VTEPs are sending based off those type 10 routes that they received, those are PIM SSM joins. So we know the source. We don't need the rendezvous point to do source discovery for us, right? So we're just sending the joins directly to the spine in this case, saying, hey, give me this IP, comma, this group. Good to go. There's no need for source discovery. So again, SSM does not require an RP. So in the EVPN domain itself, we don't require the use of an RP because we're using SSM. And this is just on here as a little note in case nobody's noticed it yet. We haven't even enabled PIM in the overlay, right? So in VRFA, if we go on the VTEPs, the leaf switches, PIM isn't even running in the VRF in the overlay, right? So just kind of want to draw that point, kind of draw attention to this because it wasn't explicitly stated yet. So I just wanted to bring attention to that. But this one, there's no real scenario for this. This is simple. Where's the rendezvous point? There is no rendezvous point. That's a wrap. Alex, Russ, anything to add to this?
Not to this one, I don't think.
All right.
Oh, good, Rich.
This is the easiest one of the day. All right. So this is the last question, guys. And I'd say we're doing pretty good. So this one is, how do we actually connect this EVPN multicast domain to an external PIM domain? And as we saw, the answer is the PEG. So the PIM Edge Gateway. We'll see that to configure the PEG, there's really not much needed in the way of any special configuration like PEG on. That's not really a thing. Really, but the VTEP, if it has a PIM adjacency on a VRF member interface to the external PIM domain, it's a PEG. And it will advertise that PEG capability via the type 3 route. Now, we could have a couple boxes that are acting as the PEG or more, they're PEG capable, but only one of them can be the PEG DR on a per VRF basis. And we'll see what the responsibilities of the PEG DR are in a second. But this is just going to be elected using a highest random weight algorithm, and we'll ultimately get a nice separation. If we have multiple VRFs, we can have a different device acting as the PEG for each respective VRF, so we don't have everything polarizing to one device. And then there can be multiple PEG DR candidates. All right, so before we jump into our little tail of the PEG scenario, what does the DR actually do? So first, it acts as a first hop router. So it'll register active senders that are in the EVPN domain. So if it receives one of those feeds, it'll send a PIM register message to the rendezvous point in the external PIM domain, just so it's aware that there is a sender of source active. It is also going to receive the SMET routes from the EVPN domain and then ultimately originate PIM joins to the external PIM domain based off of the groups that are listed in those SMET routes. So it's going to originate the PIM joins out into the external PIM domain, which eventually should make their way up to the RP if it's like an ASM join. But then also, what about the other devices that aren't necessarily the DR? What can they do? So while the PEG is responsible for the PIM register and actually originating the PIM joins out of the EVPN domain, all of the other devices, regardless of whether they're the DR or not, they can absolutely receive a PIM join from the external PIM domain and then send the SMAT route for that S, G into the EVPN domain. Right? So just because a device isn't the DR doesn't mean it can't receive a PIM join from the external PIM domain. That's totally fine. All right, so this is the home stretch, guys. We're going to go through the tail of the PEG, and then that's a wrap for the series. All right, so here we have our setup here. Leaf 5 and Leaf 6 are both connected to the external PIM domain, VRFA. And we see there's a rendezvous point out here, and then we have a host out here. Sender or receiver, doesn't matter. First, let's configure it. So the configuration here, we are going in, and on the PEG, we are going in and saying, okay, well, here's the RP under the PIM configuration for VRFA. We're defining the rendezvous point. And then if we want, we can say when I send PIM register messages, source them from this interface, which in this case, loopback 1 is an interface in VRFA. Then we're going to whatever interface is locally connected to the external PIM domain, and we're making sure it's in the VRF, and we're enabling PIM. And that's the config, right? That's not too bad. But let's see what happens now. So we've put that configuration in. Now Leaf 5 and Leaf 6 are both like, hey, I'm a PEG for VRFA. All right. So they communicate that via the type 3 route. And that type 3 route, we now see there's some additional capabilities. And we have the multicast flags PEG, and we also have DF election highest random weight. So that's the algorithm that'll be used to elect the DR. Leaf 6 sends the exact same thing, of course, with his own information, his own IP address, right? But he still says DF election, highest random weight, and peg capable. All right. Well, one of them has to be elected. So highest random weight, algorithm runs, Leaf 5 wins, right? So I won the election. Leaf 6 begrudgingly says congratulations, and I'll go do DR stuff, right? So get to work. But if we want to validate this, we can say show PIM EVPN gateway DR. Leaf 5 sees that he is the DR for VRFA. So again, there's that SBD popping back up again. So he is the DR for VRFA. And then over here, Leaf 6 is the non-DR, and he sees the DR is actually Leaf 5. All right, so we put the little peg DR badge on the switch. It's official. So now he needs to make sure that, again, one of the responsibilities is if there is an active sender in the EVPN domain, well, it needs to send the PIM register to the external PIM domain RP. So it needs to figure out a way, how do I make sure that regardless of whether or not I have any locally attached interested receivers, I need to make sure I always get any feed that's being sent, any overlay multicast feed for VRFA. And the way it's going to do that is it's going to, all right, you know what? I'm going to send a type 6 SMET route. And I'm going to, for the S comma G, before we saw there was star comma group, the peg is just going to say, you know what, star comma star. I don't care who is sending, and I don't care to what group. If it's an overlay multicast feed in VRFA, I need a copy of that. So it's going to send an SMET route to say, hey, for VRFA, I want to make sure that I don't care who's sending or what they're sending to. Please make sure that you send that feed out into the PIM underlay. So VXLAN endcap it and send it out. That's half the battle. But Leaf 5 also needs to make sure that he's going to receive those feeds, those underlay multicast feeds, right? So whatever, when this guy, Leaf 1, performs the VXLAN endcap for a overlay feed in VRFA, it's going to send that out again to 2221, comma, 232.0.0.1. That's to use that in the underlay. So just like we saw before, the peg needs to say, all right, well, I need to send a PIM SSM join for all the underlay multicast groups associated with VRFA multicast traffic. So how does he do that? And it's our old friend, the type 10 route, right? Same thing. Those type 10 routes that have overlay to underlay group mappings, we have them right here for the VRF. So Leaf 5 sends the PIM joins up to the spine. Just like we saw Leaf 1 do earlier, he's going to say, you know what? I want to join all of these S comma G, so 2221 to this group, 2222 to this group, so on and so forth. It's going to join these. So now it'll receive the feed. So when host 4 comes online and starts sending to this particular group, remember in Leaf 5's SMET route, he said, I don't care who's sending and I don't care what they're sending to. Please make sure this gets sent out into the underlay. Leaf 4 reacts accordingly and says, okay, you got it, man. Sends it up here to the spine. There's the outer IP header. That is a S comma G that Leaf 5 has joined. And as a result of that, it's sent down to him. Leaf 5 says, aha, there's an active sender in VRFA. I need to send the PIM register message out to that external PIM domain. I need to send it out to that PIM domain's RP, which is exactly what he does. So this little green line represents the PIM register. The PIM register is received, and the RP now knows of the sender. So if someone in the external PIM domain wants to receive this feed, if they send a star comma G, it makes it to the RP. The RP can then build the shared tree towards the sender. So next, other responsibility of the peg, excuse me. And then it's going to say, okay, well, I also need to make sure that if I receive an SMET route, so if there are interested receivers in VRFA and the EVPN domain, I got to make sure the external RP knows that there are receivers over here that are interested in some feed, right? Whatever that feed is, some group. So in this case, we have an interested receiver that wants to receive the group 239.1.150. It's an ASM join, doesn't care who's sending to it, just wants this group. Leaf 1, as expected, sends the SMET route saying, hey, just so you know, there's an interested receiver over here, and it's for star comma 239.1.150. Leaf 5 receives that SMET route and says, aha, someone out there in VRFA wants this particular S comma G multicast feed. Well, better make sure that the external PIM domain knows about this. So it sends the PIM join messages, which eventually make their way up to the rendezvous point. So the rendezvous point becomes aware that someone out there is interested in receiving this feed. They don't care who's sending to it. So it's a wildcard, star, comma, 239.1150. And those are really the two primary responsibilities of the PEG. So in summary, how do we connect to an external PIM domain? The answer, the PEG. As we saw, there's no real special configuration outside of enabling PIM on the VRF, and specifically on a member interface in that VRF and establishing in a PIM neighbor adjacency. Ta-da, PEG. The capability for a device to act as a PEG is advertised as part of the IMET route, so part of those multicast flags. And then we have a PEG DR elected per VRF, and we saw what the responsibilities of the PEG were through our little examples there. One last fun fact, and we'll wrap it up. For the PEG, when the PEG is sending overlay multicast traffic into the EVPN domain, it doesn't have any bridge. In our case, the PEGs, they don't have any VLANs locally present. There's not any VLANs created on the box. So what do they use? In that case, it'll actually use the L3 VNI associated with the VRF in the VXLAN header. If it receives a feed from the external PIM domain, it needs to send it into the EVPN domain. So it'll VXLAN end cap it. But this is kind of that one exception to using the bridge domain associated with the sender, because in the PEG, that bridge domain may not even exist when it receives it. So it's not, we'll see that in the PEG's case, it may use the L3 VNI in the VXLAN header instead of the L2 VNI. That's more of just a little quick fun fact. But aside from that, we made it, guys. That's a wrap. A little bittersweet. Concludes the EVPN VXLAN webinar series. Again, all the recordings are posted here. I know we went a bit over today, going out with a bang. But I want to call out that the diagram and configurations will also post those. So if anyone's interested in the configs and kind of having the diagrams to map to those configs, I will get those posted out there to the link on the screen. So thanks again, everyone. This has been a heck of a lot of fun. Alex, Russ, any outstanding questions? Anything you guys want to add before we wrap up?
All good from my side, Mitch.
Yeah, sure.
All right.
You want to add
Well, in
anything
that
else?
case,
Wrap?
boom, there it is. Thank you.
Good job.
All right,
Mitch.
guys. Well, that's a wrap. Again, thanks everyone. And yeah, we'll go ahead and sign off. Take care, all.